right? During 1870s to 1880s, the first gas engine was developed, right? With the introduction of electric ignition. So there are several methods that you can use to start the ignition. We will not be talking much about the ignition systems. Then the introduction of the Otto cycle. So this is a key element, right? The Otto cycle. We will be talking more about the Otto cycle. For now, if you do not have any idea about the Otto cycle, do not worry. So the Otto cycle led to the development of the four-stroke engine, and which is still the fundamental of most engines, right? So it marked the key benchmark, I would say, for the internal combustion engine. Then automobile applications started to innovate, like people like Carl Benz introduced the engine, and also Henry Ford started developing commercial vehicles, right? So Daimler Benz were some of the very first companies to develop the cars using petrol. After that, during 1892 region, the diesel engine was invented by Rudolf Diesel. So diesel engine introduced the compression ignition technology. So far, what we used or what we had was we needed a separate ignition source, right? For petrol engines, we needed a spark. Basically, we needed the ignition source. For diesel engines, with the invention of the diesel engine, we got rid of that. We do not need ignition source for diesel engines, so that was a improvement. With the introduction of the diesel engine, people understood that the diesel engine had the capability to provide more torque. Therefore, people started to build on ships and large vehicles which can carry cargo. Likewise, the introduction of the diesel engine helped to innovate or broaden the transportation sector further. Okay, so widespread adoption in cars, trucks, likewise, generators. Most of the generators are diesel engines, right? Even in, I think, Kalanithisa power plant, we have diesel engines, right? So performance and efficiency, apart from gas turbines, sorry, performance efficiencies and advances. So advancement in fuel systems, turbocharging, electronic ignition, and emission control technologies. So during the 1950s to early 2000 region, the concerns were rising regarding the emissions from cars and vehicles, basically, because when we burn fossil fuels, the primary output is carbon dioxide and H2O and other NOx gases. So these gases contribute significantly towards greenhouse gas, resulting in increase in greenhouse gases, which results in the increase of global warming potential. So therefore, scientists understood that we need to control these emissions. So during that region, vehicle manufacturers focused more on reducing emissions while maintaining the same performance levels from the engines. So therefore, that led to the development of modern introduction of vehicles. And during 1998, Toyota introduced the first Prius. So likewise, the hybridization, I would say, and the emerging of the EV technologies were started during that era. Focus on reducing emissions, improving fuel efficiency, and integration with the hybrid and alternative fuels. Don't worry, we will be briefly talking about these technologies also at the latter stages. So if you look at the evolution of the other supporting technologies, so there were different fuel sources. There were engines which could operate with different fuel sources, for example, gas, coal gas, and hydrogen. Then the spark plug went through many innovations, right? We do not straight away come up with the spark plug that we had today. And the ignition system, we had the distributor ignition system. Then we had coil on plug system, right? We had the waste spark system, right? If you study the evolution of the ignition distribution system itself, it went through several phases. If you consider early vehicles around 1930s, 1950s, vehicle had distributor systems, right? The early vehicles from 1950s around had the ignition system, which had a distributor, right? Basically, it's a spinning disc which comes into contact with the contactor and gives you the spark to each cylinder. Then we had the waste spark system, which is sort of basically a little bit similar to having two distributors, but it is not exactly. So the spark is distributed at once into two cylinders. So one spark will be wasted, right? So out of the two sparks, you only get one power stroke, and the other spark plug will be still creating the spark, but you do not get any power out of that spark. So that system we call the waste spark system. Then finally, we what we mostly have commonly today is the coil-on plug system. So each spark plug has the connection, gets the electronic signal, and creates the spark individually. Therefore, you do not have a complex mechanical connections or all of that. You can get rid of all of that, and you need a simple electrical circuit, and you can individually control each of your spark plugs. So that is a simple breakdown or evolution of your ignition system. Then the introduction of the four-stroke cycle. So that is a key, I would say, a breakthrough, because we had most commonly, we have two engine types, two-stroke engines and four-stroke engines. So the two-stroke engine has its own advantages and disadvantages. We'll talk about those in the latter stages. But what is commonly used for vehicles, not commonly if we consider today, modern day vehicles, every vehicle is a four-stroke engine vehicles. You don't find two-stroke engine vehicles. So then the transportation revolution. So with the introduction of the engine and the availability of the fuel, people tend to buy more and more vehicles. And also there were improvements in terms of safety, like uh, for example, companies like Volvo focused mainly on the safety. They introduced the 3-point seatbelt system, and they did not patent it and made it available for all of the manufacturers like freely. So that likewise, some companies focused mainly on the vehicle safety. So for due to the reasons like that, the transportation or the car became gradually popular. Then the diesel innovation, as we discussed before, diesel engines were capable of providing higher torques rather than the petrol engines, so that the diesel engine was equipped to carrying large loads. Okay, then mass production and global use. Yes, the manufacturing technologies were evolving with the industrial revolutions. The manufacturing processes were getting more efficient and less labor relied, right? So they were more machine focused, right? There were many automation processes happening. So the automobile manufacturing process was getting more streamlined, right? So it was the output from the factories were steadily increasing. Technology enhancements, yes, like turbochargers, superchargers, electric turbochargers, likewise. There are many new technologies that were coming into the industry that help to increase the performance characteristics, I would say, of the vehicles. And finally, after the early 2000s, people were getting more concerned about being eco-friendly. So therefore, the automobile industry was turning towards more sustainable path. Okay, so to reduce emissions, alternative fuels, electrification, and hybrid integration. So the internal combustion engine, as a summary, has powered industrialization, global transportation, and economic growth for over a century and continues to evolve toward a cleaner and more efficient future. Yes, we consider the car, it provides a many useful properties or services while being efficient, right? That is the sign of a good machine, right? It should do the a task it is intended to, while being efficient. So efficiency simply means what you give as the input and how much you get as the output, right? That ratio, output over input. So whatever you give as the input, you should get the maximum as the output. So a vehicle has a considerable efficiency in terms of the input and output. Okay. Yeah, so these are the some of the pioneers in terms of commercial vehicles. So this picture shows you I don't know whether yeah, I hope now you can see. So this picture is the picture of Carl Benz. So one of the first people to develop petrol cars, and this is the picture of Henry Ford. So if we think about the Ford company, so Ford Model T was the first mass-produced car, and actually Henry Ford, with his involvement, was the one of the first pioneers to introduce batch line, like manufacturing lines, streamlining the process. So they were able to, I don't exactly remember the value. I think they produced around 8 cars per day, right? So with that, they could make the cars more cheaper and more available to the community. Okay. And if you think about it, with the uh, around close to a century, with the age gap of close to less than a century, the vehicles have evolved up to this, right? This is a 2024 5 Ford Mustang. So it's a muscle car which has very high performance characteristics, right? So we have a V8 engine, V10 engine, depending on the version, right? It has a very high safety. So you can compare the two cars. Okay. So I'll take this opportunity to discuss one more external parameter. So I think you might have heard like people of metal, they were strong, and when they were in an accident, they do not break, and they compare to these cars, right? Calling the cars today, which are flimsy, they are made out of plastic likewise. So I would like to know your opinion about that. What do you think? Were the cars better then, or the cars what we have today are better? What is your opinion on that? Okay, so you're saying today cars, what we have today are better. Do you know the reason? Are you just saying because we have larger engines, we have better cars, more power than the older cars? Yes, the primary parameter is the safety. So in older cars, yes, they are more rigid, they have more strength, they were made out of metal. But in an accident, the car might not get hurt, but the passengers are the people who will get the damage, right? So older cars did not have the concept of what we call a crumple zone. Okay, so what we have is a crumple zone. So today cars are designed to have a crumple zone. So the first crumple zone will be on the front, right? The very front, the engine bay and the bonnet. So if you think about this bonnet, it is a sheet metal, okay? It's manufactured using sheet metal. You might have seen some corrugations in the middle, right? There are some parts which like bending marks which goes throughout the middle. So that is a tested procedure to, in case of an accident, the bonnet won't slide back into the compartment, right? As a whole, it will not never uh, compress back onto the compartment. If it did, it'll act as a blade and cut your neck clean off, right? That's what used to happen in older cars. If this car gets into an accident, there is a risk of this bonnet sliding inside the passenger compartment. If that did happen, that will sever your neck basically, right? So this bonnet is designed so that the middle part of the bonnet is weaker than actually the front, so that when it is in an accident, it will crumple, right? Like what you call, what we have is a papadum, right? What we eat, right? So it does not it absorbs the collision and reduces the risk of, it keeps the passenger compartment safe. Okay. And similarly, at the back, you have what we usually call the trunk or the dicky, right? So that is also a crumple zone that can absorb the impact. The doors have these bars, everything. The roof is designed so that it can absorb the compact and leave the passenger area safe. Okay. So if you hear anyone talking about or comparing older vehicles to today vehicles, saying that they were made out of metal and today vehicles are made out of fiberglass or plastic. So what they're saying is true, but that process has been done due to a reason, and they do a lot of analysis when they're designing a car. Okay. So keep that in mind. Okay, so now we can talk about some of the terminologies, some terms that I might use throughout the lecture. So don't worry. If you do not understand anything, feel free to ask. So what we have is first is the bow, right? So bow is what you call the diameter of the cylinder. So when you take or when you consider the engine, you have several cylinders, right? You have four-cylinder engines, six-cylinder engines, eight-cylinder engines. There is a reason why these are even numbers, okay? Four, six, eight. Very so nowadays, three-cylinder engines have become common. In the older days, there were five-cylinder engines. Today, I don't remember a car which has a five-cylinder engine, but I heard about a BMW or a Porsche, I think. I'm not sure. So usually these days we do not find odd numbers as the number of cylinders. There is a reason for that. The primary reason being the engine balancing, right? So when the engine is running, there are a lot of forces generated within the engine. We need to balance these forces out. Else, what would happen is that the engine will have very large vibrations, right? You won't be able to drive the car. The car will be like shaking. So unless you balance the engine, your engine mounts also designed to absorb these vibrations to a certain extent, but still your engine is critically balanced due to the forces generated within the engine. Okay. So if you have even number of cylinders, it is easier to balance the engine. So for the most part, that's why we did not have three-cylinder engines, but now engineers have come up with a solution to balance the three-cylinder engines. Therefore, it is becoming quite popular, right? So we can reduce the emissions by using a three-cylinder engine. Therefore, these three-cylinder engines are becoming quite popular. So, okay, so the bow is the diameter, which is basically this diameter, right? The diameter of the cylinder. Stroke is the distance the piston travels from TDC to BDC. So as to what is TDC is the top dead center and BDC is the bottom dead center. So TDC is the top dead center, which means the highest point which your piston travels to. Your piston never travels further than the TDC. It stops when the crankshaft and the connecting rod are aligned. So this is what you call the connecting rod, and this is from your crankshaft. Don't worry, we'll be talking about these components further in the future. So when all of these are aligned, the maximum height is what you get as the top dead center. And the bottom dead center is the lowest point where the piston can travel to. So that is the limit where your piston is traveling. In between these two heights, your piston will be traveling up and down. In each stroke, it will be traveling up and down. So this distance is what you call the stroke length. Okay. So swept volume is the volume covered by the piston during the movement. So when the piston is going from BDC to TDC, it will cover the height of the stroke, right? And if you think about the cross section of the cylinder, it is a circle, right? So we know the diameter and the cross section is a circle. So what you get when you multiply a circular cross section by a height, you have a circular cross section and you have a height. Now what do you get from TDC? If you imagine the TDC to BDC height with this circular cross section, you get a cylinder, right? So that cylinder volume by R squared H is a volume of a cylinder. So your H or the height is actually the stroke length, and your R is actually the half the bore diameter or the bore radius, right? So from that, you can get the swept volume, what we call the swept volume, right? These are international terminologies, irrelevant of the country you are in. These terms will mean the same thing. If you are talking about engine, TDC will be the same thing and the BDC will be the same thing. Unless it is a horizontal engine, which we call a boxed engine, the cylinder is vertical, right? If the cylinder is horizontal, you have a slightly different term, but there are very rare you will come across a horizontal engine. Okay, so the clearance volume. Clearance volume is the volume remaining when the piston is at TDC. So I mentioned that the piston will never pass the TDC. So when the piston is at the TDC, you can see here there is a slight volume remaining between the two, between TDC and the top of the piston, top of the cylinder. You have a slight volume. So this volume is what we call the clearance volume, and there is a purpose for this clearance volume. This clearance volume is kept to ensure the safety of your valves. Okay. So if you did not have the clearance volume and if the piston was allowed to reach the top of the cylinder, there are certain situations where your valves are kept open, right? So if you did not have the clearance volume, in some scenarios, you have the risk of the piston coming into contact or hitting the valves, right? So if such thing happens, you're going to destroy the valve system, valve assembly, and you're going to damage your pistons, right? So that scenario should be avoided at all costs. Therefore, we have to maintain a clearance volume. Then the engine capacity, right? So depending on the number of cylinders and the volume of the cylinder, you can decide on the engine capacity, total swept volume of all cylinders. So if you can calculate the swept volume of one cylinder, then you have to multiply that by the number of cylinders, depending on whether it's a 4, 6, 8, 10, 12, or 16 cylinders. So you have to calculate one swept volume and you can multiply it by the number of cylinders, which is N. Then you can get the capacity of the engine. So this capacity, engine capacity, we generally use the units of cc, which is cubic centimeters, or L, which is liters, to talk about the engine capacity. So I hope you guys remember 1 cubic centimeter is equal to 1 milliliter. Therefore, we can convert this easily. So I hope you guys are familiar. We talk about 1000 cc engines, right? So 1000 cc engine would be a 1 liter engine. 1000 cc engine would be a 1 liter engine, right? So similarly, if it is a 2000 cc engine, the capacity will be a 2 liter engine. So you might have heard 1500 cc, then it becomes 1.5 liter engine. Then depending on the air intake, you might have heard the term naturally aspirated engine, right? So that is another term associated with when we are talking about engines. Naturally aspirated engine. So naturally aspirated means there are no turbochargers or superchargers. Your air intake depends solely on a simple air intake, right? The filter goes through the filter and comes through the inlet manifold. There are no technologies to improve your inlet airflow. If you have turbochargers, we call it a turbocharged engine. If you have a supercharger, we call it a supercharged engines. And some very few high-tech engines, performance engines, may have turbochargers and superchargers both together. Okay, so that's depending on the engine intake. Okay, so when you're talking about engine capacity, that's how we mention about the engine capacity. And also, if you have heard the term inline V10, W16, so these talk about the cylinder arrangement. Okay, so we'll be talking about that at a later stage as well. So there is another important parameter which I think I should discuss based on the swept volume and the clearance volume. So there is a term called the compression ratio. Okay, CR, compression ratio. So compression ratio, I'll type it in so that you can do a self-study on the topic. So this is another important parameter, the compression ratio. So compression ratio means the maximum volume of the cylinder, the total volume of the cylinder, the ratio between the total volume of the cylinder to the smallest volume of the cylinder. So your largest or the total volume of the cylinder will be the addition of the swept volume and your clearance volume. Your smallest volume in the cylinder would be just your clearance volume. So by using that, you can calculate the compression ratio. For all cylinders, this would be the same. So the importance of the compression ratio is that compression ratio is small for comparatively small for petrol engines, while the compression ratio for diesel engines are higher. So, for example, if you think about the compression ratio of a petrol engine, it ranges about from 8 to 1 up to 12 to 1, right? Some very high performance engines may go up to 14 to 1, but usually what you find are the compression ratio in a region between these two values. But if you consider diesel engines, the compression ratios will start around from 14 to 1 to around 22 to 1, right? So the compression ratio, this is for petrol engines, 8 to 1 to 12 to 1. And for diesel engines, the compression ratio is for 14 to 1 to 22 to 1, around 20 to 22 to 1. This is primarily because your petrol engine does not solely rely on the compression for the ignition, right? For a petrol engine, we have a spark plug, therefore we have a ignition source. But for a compression ignition engine or a diesel engine, air fuel mixture gets or starts to burn due to the compression, right? Therefore, we need to have a higher compression ratio in order to achieve the combustion. Yeah. And also the compression ratio affects the efficiency of your engine as well. Okay. Yeah, so if we have a look at the components of engine, so this is a cross section of would you like to guess what is the cross section? What type of engine is this? Is it a diesel engine or a petrol engine? Okay, so I have one question. How does the compression ratio affects the engine efficiency? So I'll discuss about that with the introduction of the cycles, I think, rather than here. So you guys would understand a little bit better, right? So that has something to do with what we call thermodynamics. So when we are discussing the topic or the principles of thermodynamics, I'll explain how the compression ratio affects the efficiency. So bear with me, and I'll explain it in the future. Okay, so what do you guys think? Is this a petrol engine or a diesel engine? Oh, I have been messaging only one person. I thought I was putting it in the forum. Sorry about that. I think you can share it with your mates about the terms I have spared. Yes, so moving on. This is a diesel engine. Why? How do we decide that? So basically the fuel injector, right? So if it was a petrol engine, you do not have the fuel injector. You might have the fuel injector, but primarily there needs to be a spark plug, right? So here you cannot see a spark plug. Therefore, you have to understand this is a uh, diesel engine. So here you have a turbocharger. That is an additional component which we will talk about later. So if we think about the engine, there are three main components, right? Where you can focus on. One is the oil pan, right? That is the first part, first section. Then you have the engine block, what you call the engine block in the middle. That is the second part. And on top, the top assembly is what you call the engine head. So engine head holds the valve assembly, right? This is the oil pan. And then you have the block, engine block in the middle. And on top, you have the engine head, where you will find your valve assembly, right? Your inlet and exhaust valves is found in the engine head. So the main components here, you have the crankshaft. So your crankshaft is responsible for transmitting the reciprocating motion of your pistons. So reciprocating means just going up and down, repeatedly moving up and down. So reciprocating linear movement is converted into a rotary motion, and this rotary motion is maintained and continued by the crankshaft given to the flywheel. You store some energy in the flywheel, and this is transmitted through the gearbox to your wheels, right? So your crankshaft is a very major component of your engine. Then the crankshaft is connected to the connecting rods, right? So through the connecting rods, to the connecting rods, your piston is connected to your connecting rod. So it runs within the cylinder. Then you have the camshaft. Depending on the location of the camshaft, there are several types of engines which we will be discussing in future. And this particular arrangement, you have a push rod and a rocker arm mechanism to activate the valves, right? So these are the valves. You will have two valves, depending on the engine. You may have two valves per cylinder, sometimes four valves per cylinder, meaning two for intake and two for exhaust. That is a design parameter which the engineer will design on how many valves that you need to ensure the proper flow. So fuel injector, which introduces the fuel to the system, and you have a fuel pump, and a glow plug. So the purpose of the glow plug is to in cold start scenarios where the environmental temperature is low and you need to start the engine, the heat generated just by the compression may not be sufficient. In that sort of scenarios, you need to preheat the engine to gain some thermal energy within the, or build up some thermal energy within the engine. For that, you can use the glow plug, right? So that is directly near the combustion chamber, so that the air fuel mixture will start to combust with the added heat. Okay. So these are the main components of a diesel engine. Most of the things are similar in a petrol engine as well. The only or the primary difference will be the spark plug, right? So here you can see directly to the combustion chamber, we have introduced a spark plug. So we need the spark plug to initiate the combustion in a petrol engine. By that, we can identify the petrol engine from a diesel engine. So this engine has a V arrangement, right? This we call a previous engine was a engine. So everything is straight, right? You can see the piston is straight. So all the pistons in this engine would be straight or vertical, right? And inline. They are all inline. So we call it an inline. If it is 6 cylinders, we call it an inline 6 engine. If it is a 4 cylinder, we call it an inline 4. Likewise, the arrangement, based on the arrangement, we call it a inline engine. In here, you can see the pistons are forming a letter V, right? So we call it a V engine, depending on how many cylinders you have. If you have 6 cylinders, we call it a V6 engine. If you have 8 cylinders, we call it a V8 engine. So likewise, that is based on the engine arrangement. So apart from that, this also has a camshaft which is operating from pushrod and rocker arm mechanisms. There are other methods where you can initiate or control your valves, right? This is only a one arrangement. Other components, the basic configuration is similar for both engines. You have the bottom, you have the oil pan, right? So some high performance engines, mainly like rally cars, where the oil pan can get damaged easily, and in high performance vehicles, there might be dry sump vehicles, right? So if you find a dry sump engine, that means you do not have a very large oil pan. The oil pan will be very, very thin, right? Very shallow, right? Not this much deep. So the engine does not hold that much of the lubricant, which is the engine oil, right? That sort of arrangement we call the dry sump engine, right? So usually what we find in commercial cars are mostly having a large oil sump. The other parameters or the configurations are the same. In the middle, you have the engine block, and the top, you have the engine head. So in this particular V arrangement, we need to have two separate engine heads for the two separate sides, right? So in an inline engine, we only had one engine head, but for the V arrangement, there are separate two engine heads, and you have your inlet manifold, where we call the inlet manifold is the manifold. Manifold is just a shape, right? So it distributes the intake air individually into the cylinders, right? Whatever air is coming in is distributed through the inlet manifold. So you have the inlet manifold and you have the exhaust manifold, which acts opposite to the inlet manifold, where all the exhaust gas are circulated to the outside. Okay, so those are the main components associated with the petrol engine. Okay, we can move on to the next slide. Okay, so here you can see some of the actual components, right? So here I'll start from, you cannot see a oil sump. Apart from that, you can see many other components. So on the rightmost picture, what you have is the engine head, right? So it's a engine head. Um, so this particular arrangement, you have the camshaft on top of the head. For the previous two pictures, if you remember, the camshaft was in the block, inside the block, right? So in this arrangement, the camshaft is here within the block, nothing on top of the valves. Not There is only the rocker arm. The camshaft is located below the valves, right? So this is one arrangement. And in this particular picture, what you have is the camshaft is on top of the valves, right? So this is a valve head being assembled, right? After assembly, this is how it looks like. You have the valve springs, you have a rocker arm which is connected to the camshaft, and you have the discs, right? The cotters and the discs which are holding the valve springs tightly. Okay. So there are some manufacturing considerations and operating considerations that goes into the design of an engine. So you need to ensure proper clearance values are maintained when you're assembling an engine head due to thermal expansion, right? We know that metal expands with heat, right? We have experienced that personally. So the engine is built at room temperature, but it performs at a higher temperature, right? The engine ideally works in good condition, maybe in the region of 90 Celsius to around 120 Celsius. So you need a temperature increase, right? So with the temperature increase, the components are made out of metal. Therefore, they will expand, right? So there are manufacturer specified clearance values which you need to take into consideration when you're assembling an engine. Okay, so that's for your general knowledge or additional knowledge. Then here you can see a engine block, right? So it's a inline four-cylinder engine. You have four cylinders. All four cylinders are in a line, right? In a straight line. So we call it a inline engine. So these holes, some of them are for the engine oil and the others are for the cooling, right? Engine cooling, right? We need to keep the engine at the optimal temperature. Therefore, we need cooling. We cannot let the engine heat up uncontrolled. That will overheat the engine and cause the engine damage, right? So therefore, we need to maintain the proper temperature of the engine. For that purpose, we need engine cooling. We call it the cooling jacket. There are pathways traveling in the engine block. There are pathways which travel around the cylinders, keeping or maintaining the temperature of the whole engine. Then these are two valves which you can see. You can see that one valve is slightly larger than the other, right? So how do you identify which one is the inlet valve and which one is the exhaust valve? If you study any valve arrangement, any valve assembly, one valve will be slightly larger than the other valve. So out of the two valves, what do you think? Which valve will be larger than the other? Is the valve the larger one or the inlet valve the larger one? Out of the two valves, which valve is larger? If you study any engine, you will identify that some valves are larger than the other for a particular cylinder. For a cylinder, regardless of how many valves it has, if it has four valves, two valves will be larger than the other two. If it only has two valves, one valve will be larger than the other one. So how do you identify which is which? What do you think? Which valve is larger and why? Any guesses? So, shall I answer myself? So out of the two valves, the inlet valve is the larger valve, right? So inlet valve will be larger than your exhaust valve. In this picture, the first valve might be seem bigger because it is closer to the camera as well. But if you study any valve assembly, one valve will be larger than the other. So what is larger is your inlet valve. So inlet valve is larger to ensure proper or enough air inside to the cylinder, right? To maintain mass flow rate, we have a larger inlet valve. In the bottom picture, you can see the crankshaft, right? So if you have seen shafts, what we call a shaft is when we talk about a shaft, what comes to our mind is a cylindrical uniform cross section, like sort of a flute or a pipe sort of thing, right? But that is a common misconception. So if you look at the crankshaft, it has a very peculiar shape, right? So it has some masses. So these actually have a engineering principle or a requirement, a mathematical requirement behind this design of the crankshaft. So what you have in a crankshaft is an eccentric mass, right? What we call it is a eccentric mass. So there is a mass distribution. The mass is distribution to one side. This is to achieve what I talked about before, right? The engine balancing. So what you have is the reciprocating motion and the rotary motion. So in the engine, you need to balance the forces coming from the reciprocating motion and from the rotary motion. So the shape of the crankshaft depends on how you balance your reciprocating forces and your balancing of the rotating masses. Okay. So if somebody asks you why the crankshaft has such peculiar shape, it is to balance out the vibrations that could occur in the engine. If you use a simple uniform cross section shaft, there will be a lot of vibrations. You'll damage your engine. Basically, you cannot run your engine, right? Therefore, to balance out the rotating elements and the reciprocating forces, the elements, you need to have this shape. Okay. Okay, so then so far what we have discussed is about the terminologies associated with the internal combustion engine, and then some mostly related to the manufacturing concerns of the internal combustion engine. So now we are going to encounter or discuss about the working principle of the internal combustion engine. So as the term suggests, uh, the uh, internal combustion engine relies on primarily on the principles of thermodynamics. Okay, Tapa Gati Vidya, Tapa Dynamics Gati Vidya. Okay, the science, thermodynamic science. So what thermodynamics is nothing complex. Thermodynamics just simply talks about the energy flow, right? Thermodynamics is talking about the heat energy, what happens to the energy in the system. So we understand that the internal combustion engine converts thermal energy generated by the combustion fuel into useful mechanical energy. So combustion happens inside the closed chamber, and fuel can be in liquid and gaseous state. Yes. So if we think about a petrol engine, we have the air fuel, right? Air fuel mixture coming through inlet manifold, right? It gets inserted into the cylinder and gets compressed. When in compression, the spark plug ignites the mixture and the mixture starts to combust. When the mixture is under combustion, combustion is occurring, the piston is pushed down, right? And this pushing down is converting the energy into the rotational motion at the crankshaft. And after the combustion, the exhaust stroke occurs, and the combustion elements, the resultants, are pushed out of the cylinder through the exhaust valve. So what basically happens, or the starting point, is first the chemical energy. You start with the fuel, which has the chemical energy, and during the combustion process, you are converting this chemical energy into thermal energy. And when the power stroke occurs, when the combustion occurs, your piston is being pushed down by the combustion gas. Therefore, you are converting this thermal energy into the kinetic motion of the crankshaft. Basically, you are converting this energy into mechanical energy, right? So your inputs to the system are fuel and air. Even if it is a diesel engine, what you need to input is fuel and air. And you have to introduce an ignition source, right? A uh, a source which can start the ignition, right? The spark plug, then you can get out the result will be the combustion process. Okay, from the combustion you can get the mechanical energy. So it's a simple energy conversion. Okay, so if we talk about thermodynamics, the first law of thermodynamics is the conservation of energy, right? That means the සිංහලෙන් කිව්වොත් ශක්ති සංස්ථිති නියම. ඕක තමයි තාපගත විද්‍යාවේ පළවෙනි නියමය. The first law of thermodynamics is just energy conservation, which means that the energy cannot be created nor destroyed. It can only be converted from one form to another, right? ශක්තිය මවන්න හෝ විනාශ කරන්න බෑ. අපිට පුළුවන් වෙන්නේ ශක්තිය එක් ප්‍රභේදයකින් ඉඳන් තවත් ප්‍රභේදයකට පරිවර්තනය කරන එක පමණයි. There are no engines or power generation elements which generates power out of nothing, right? So even though you might see on TV or the internet, like people claiming to generate energy out of nothing, right? I remember a few years back, there were people in Sri Lanka who had a mercury motor or something, right? So even if you see, even if it seems like it acts on no energy, there should be, they have hidden energy source somewhere, right? You cannot get what basically the first law says is, you cannot destroy or create energy, right? මවන්න කොහෙන්වත් මවන්න බෑ එනර්ජි එක. අපිට අනිවාර්යෙන් සෝර්ස් එකක් තියෙන්න ඕනේ, අවුට්පුට් එකක් තියෙන්න ඕනේ. එහෙම නැතුව then you have the second law of thermodynamics which states that there is no engine which generates energy out of nothing, right? මුකුත්ම නැති තැනකින් ඔයාට ශක්තිය එළියට ගන්න බෑ. ඔයා මොකක් හරි ශක්තියක් දුන්නොත් ඒකෙන් කොටසක් ඔයාට එළියට ගන්න පුළුවන්. ඔක තමයි thermodynamics laws වලින් state කරලා තියෙන්නේ. Okay. So moving on, yeah. If you remember when we were talking about the evolution of the engine, I mentioned that the introduction of the Otto cycle was a breakthrough. So this is the reason that I mentioned that the Otto cycle was a breakthrough. So Otto cycle is the thermodynamic cycle of the petrol engine, right? So if you have a petrol engine, it runs on the Otto cycle. So a thermodynamic cycle is a process where your working fluid goes through some state changes and gives a resultant output, right? So it might go through heat energy. You have heat energy, you have internal energy, and you have your work, right? So the engine, when going through a cycle, we convert the heat energy into mechanical work, right? To convert the heat energy into the mechanical work, we need a cycle. Basically, there needs to be a process. We cannot, so if you think about the boiling of the kettle, just because we boil the kettle, we cannot take a work output, right? Just because we boil the kettle doesn't start moving, right? So similarly, just because you combust the fuel, the things won't start working. You need to have a controlled cycle where you get or where you convert this heat energy in a controlled manner into mechanical work. Otherwise, you cannot get the optimum work output from the system. Okay. So the introduction of the Otto cycle, the credit goes to Nicholas August Otto. I don't exactly remember the time period. It was, as I remember, around 1800s, right? So a long time back, but still the primary or the principle of the engine is the Otto cycle for the petrol engine, which is the spark ignition engine. So if you look at the cycle, this is what you call a PV diagram, right? In thermodynamics, we call this a PV diagram. P being stands for the pressure, right? So V is standing for volume. So it's a pressure volume graph. The contemporary or the other version of this graph would be a temperature entropy graph, but that is slightly complex, and you don't need to understand the that diagram, it is better if you can understand this diagram. So you will be starting with your intake stroke, right? So as you propagate, starting from 0, going to 1. If you look at the x-axis, which is the volume axis, so in during the intake stroke, what happens is your piston goes down, right? So as your piston goes down, basically means your volume is increasing. So it should travel on the x direction. It travels on the x direction up to a certain volume, right? This will be your maximum stroke length, right? It will stop there. Then after the intake stroke, what you have is the compression stroke, right? So during the compression stroke, your volume starts to reduce, right? The piston is coming back now. So the piston is coming back, the volume is reducing, but inside your cylinder, now you have the air-fuel mixture which was introduced in the intake stroke. Due to this air-fuel mixture is now getting compressed, meaning the pressure is now increasing, right? So the pressure is increasing to a certain point. After it has uh, compressed to a certain degrees, we introduce the spark and start the combustion. From 2 to 3, we have a constant volume. If you look at the x-axis, the volume of the volume does not change from 2 to 3. It's a fixed volume, right? So we call it a constant volume. Q stands for heat, constant volume heat addition. We consider the combustion occurs at a constant volume, meaning the position of the piston does not change. During from 2 to 3, the piston is stationary, which is a small time gap, right? So during this process, it is a constant volume process. The heat is added, the combustion is done. Then from 3 to 4, we have the power stroke, meaning now your piston is being pushed down, right? So as the piston is being pushed down, your volume is again increasing. And as the volume is increasing, your exhaust gas is now expanding, right? So therefore, your pressure is reducing, right? Again, it comes to the what do you call the maximum stroke length, right? The BDC. Then you have the heat removal. The exhaust valve opens and the exhaust gases are pushed out. So then under a constant volume, uh, 4 to 1 happens again in a constant volume and gets the exhaust gases are pushed out. And this cycle, exhaust stroke goes again to the 0, and this is a constant closed loop, right? It goes from 0 to 1, 2, 3, 4, 1, back again to 0, 1, 2, 3, 4. So this is the ideal graph which we use to design the engine. We can decide on the pressures, right? We can decide on the volume and develop the engine. So this is the practical graph. So you'll start, the intake valve opens at a slightly higher temperature and pressure, and you maintain a slightly lower pressure within the cylinder to ensure the proper airflow from the outside to the inside, right? So that the air will flow from air always flows from the higher pressure to the lower pressure. So if your atmospheric pressure is higher, then air in the atmosphere will try to come into the lower pressure. So therefore, you need to maintain the lower pressure within your cylinder to ensure proper airflow from the outside to the inside. So as the air comes in, you end the intake stroke, then the intake valve will close and this will start to compress. So during the compression, the pressure is increasing, the volume is reducing. So near to the TDC, the ignition will occur, starting your combustion process. And you can see that even in the practical scenario, it is mostly a constant volume process, meaning the volume of the cylinder does not change during that combustion period. After the combustion, the pressure goes to a maximum and then starts to expand. and at a close to the BDC, you will be opening your exhaust valve, and the exhaust gas is let out of the system. And you'll maintain a slightly higher pressure than the atmospheric pressure. Again, why? Because gas or air or everything flows from high pressure to low pressure. So if you maintain a high pressure within your cylinder and your atmospheric pressure is low, now everything inside your cylinder tries to escape, right? So that is what we need. We need to get rid of the exhaust gases. Therefore, we maintain a slightly higher temperature within the cylinder. Therefore, the gases will be pushed out or sucked out from the exhaust manifold to the outside atmosphere. So this is the thermodynamic cycle for a spark ignition engine or a petrol engine which runs on the Otto cycle. So I mentioned about the compression ratio. So this efficiency. There are several efficiency parameters when we are talking about engine. We can talk about the mechanical efficiency, brake mean effective pressure, indicative efficiency, indicated power. Likewise, there are a lot of efficiency parameters, but one key parameter which engineers focus on is the thermal efficiency. So the eta thermal, eta is a Greek letter, the epsilon. Sorry, this is not the symbol that we use for efficiency. It's not epsilon. It should be eta. So eta looks like this, a slightly long N. So eta thermal. So that means the efficiency, thermal efficiency. So thermal efficiency for a Otto cycle simplifies up to 1 minus 1 over R to the power gamma minus 1. This is R, the bottom denominator is R, and the power is gamma minus 1. So this R stands for compression ratio. Okay, so basically your thermal efficiency relies on directly on your compression ratio. So gamma is a Cp over Cv value, which is the specific heat capacity for a gas. Okay, so that is another thermodynamic parameter depending on the gas. That's a fixed value depending on the conditions again. So this is slightly a little bit of a complex topic. If you have not studied deeply into mathematics and thermodynamic principles, it is slightly difficult to understand. So this is the expression. So when we are talking about thermodynamics, there are several cycles existing. So each power plant acts on a specific cycle, right? So your internal combustion engine is a power plant. It generates power. So internal combustion engines, spark ignition engines operate on an Otto cycle. If you think about a steam power generation plant, we call it the Rankine cycle. Okay. Then if you think about a gas turbine, if it runs on a gas turbine, we have a Brayton cycle. Then the next topic we are going to be talking is about the diesel cycle. So each of these cycles will have different thermodynamic efficiencies. And one cycle which is special, we call it the Carnot cycle. So the Carnot cycle, we do not find practically. If you are interested, you can read up more about these topics: Rankine cycle, Brayton cycle, Carnot cycle, Otto cycle, and diesel cycle. So these are some common power generation cycles which we use in thermodynamics. So Carnot cycle has the maximum thermal efficiency. We call it the Carnot efficiency. So there are no engines which goes far or achieves higher efficiency than a Carnot efficiency. Okay, so the maximum practical efficiency which we can read is what we call the Carnot efficiency. And no, it is not 100%. Carnot efficiency is still lower than 100%, considerably lower. What you have in mind, maybe 90%, 80%. No, it is a little bit still lower than that. Okay. So what we call it the Carnot efficiency. So this expression is sort of derived out of those principles. So if you like, you can look into more how you derive this expression. So this is only for the Otto cycle. So R is being your compression ratio, right? So if R is larger, if you have higher compression ratio, your fraction, what will happen to your fraction? When the denominator is increasing, 1 over 10 is you will get 0.1, 1 over 5 you get 0.2, right? So when the denominator is increasing, your fraction becomes smaller. So 1 minus a smaller value is a larger number, right? So if the compression ratio is high, your thermal efficiency will be high. That is for a petrol engine. But the limitation, there is a limitation. Then you might ask why, so why don't we go for a high compression ratio if it increases the thermal efficiency? But remember, we are talking about spark ignition engine. When you increase the compression ratio, you increase the risk of engine knock, right? What you do when you increase the compression ratio is you increase the risk of engine knock, right? So one thing as engineers, what we need to evade or we need to eliminate is this engine knock. So engine knock is basically the combustion occurring before the designated location. If the ignition occurs somewhere else, we do not get the maximum power output from the engine, right? So we lose a lot of power if the ignition point gets um, changed, right? Do not like to have, we need to ensure proper ignition point. Otherwise, we will not get the maximum power output. Therefore, if the risk of increasing the compression ratio is you will be increasing the risk of engine knock. If engine knock occurs, you will be damaging your engine, you will wear out your components and you will be losing energy, right? So therefore, manufacturers like to keep the compression ratio between a safe region. Otherwise, it's a high performance engine. There are some methods which they can use to mitigate the engine knock. We will be talking about those technologies later. Okay, so this is how the compression ratio is related to the efficiency of the engine. I hope I answered your question. Okay, then we can move on to the diesel engine. So diesel engine was introduced, the diesel cycle was introduced by Rudolf Diesel. So also around very late, close to a century period, right? More than slightly more than a century maybe. So the critical difference or the primary difference between the spark ignition engine and the compression ignition engine, if you remember. So compression ignition was a constant volume process, and this diesel cycle has a constant pressure process. You can see in the y-axis from 2 to 3, there is no change in pressure, right? So we call it a constant pressure process. The combustion occurs, the fuel addition occurs from 2 to 3, where the combustion is started. So from 2 to 3, the heat addition occurs in a constant pressure process. So you can see the simulate all the other parameters, all the other not parameters, all the other state points and the processes are similar, but the process from 2 to 3 has changed. Previously, it was a constant volume process. Now what you have is a constant pressure process. Even the exhaust is still a constant volume process. So in the spark ignition engine, what you had was two constant volume processes, but in a diesel engine, what you have is a constant pressure process and a constant volume process. So if you like to know this adiabatic compression, adiabatic is a term meaning heat losses. There is no heat energy transmitted in or out of the system, right? So we are basically assuming a well-insulated system. There are no heat transfer between the surfaces. So that is a assumption in the ideal scenario. Of course, when you go into the practical scenario, there are some heat transfers, but we can mitigate those conditions as well. So if I explain to you, from 0 to 1, we have the intake stroke similar to the before, the same scenario. Then it gets compressed. And when it is getting compressed at a certain pressure, the closer to the TDC, the fuel injector. So in a diesel engine, what you compress is just the air, right? You do not get the air fuel mixture to the cylinder. You intake stroke intakes the fresh air and compresses it. At the TDC, the fuel injector will include or inject the fuel to the combustion chamber, and the combustion will start due to the compression, right? So from 2 to 3, under a constant pressure, the combustion occurs, and after 3, you get the power stroke. And at closer to the BDC, your exhaust valve opens, and the uh, exhaust gas is pushed out of the cylinder to the outside atmosphere. So there is also an interesting uh, scenario occurring, or a design scenario occurring here as well. So once you open your exhaust valve, you close your exhaust valve at a point like around here, right? And you can see the intake valve opens around here, and the intake valve will be closing. Intake valve opens, and so intake valve closes around here, right? So for a small region, you can see intake valve is open, and up to here, your exhaust valve is also open, right? There is a small period where both of the valves are open, right? We call this the valve overlap, right? When we are designing an engine, we do this intentionally. We have a valve overlap. So valve overlap creates a scavenging effect, which means it pushes out your exhaust air and also drags in your intake air. It creates a scavenging effect, ensuring proper exclusion of the exhaust gases and proper inclusion of the intake air, right? To ensure this, we have the valve overlap, where both your intake valves and out exhaust valves are open. Okay, so those are some design considerations or things engineers have come up with. Okay, then we can move on to some how do we classify engines? Okay, so one most common engine classification is based on the cylinder arrangement, right? So depending on the cylinder arrangement, we have inline engines, V engines, radial engines, flat engines, and also there are W type engines. Okay, so there are several arrangements. Inline arrangement is simply vertical engines, vertical cylinders kept in a line. V engine will have two cylinders at the shape of a V, letter V, right? So depending on the number of six cylinders, we call it a V6 engine, V8 engine, or a V10 engine, and we also have V12 engines. Okay. Um, I think there was a Bugatti which had a V16 engine. There's only one car, I think. So it was not, it's not, or a BMW. The only the engine was manufactured. It wasn't installed inside a car. So check on that. So most common you find are from V6 to V12. Okay. So those are the more common: V6, V8, V10, and V12. Then you have radial engines. So radial engines are found in aircrafts, helicopters, maybe mostly aircrafts, propeller-driven aircrafts in during the World War II period, before the invention of the turbines. What we have in today's aircrafts are gas turbines, right? So before that, before the invention of that, and before the incorporation of that, we had radial engines, which could give you the rotary motion, right? Then flat engines or Boxster engines. So those were most common in Subarus, right? Subaru was the company that introduced the Boxster arrangement, and you have Porsche 718, which incorporates. So if you consider modern day vehicle, one car is the Porsche 718 Boxster. So you can find the Boxster engine arrangement. Then, depending on the method of cooling, you can call. So, how do you cool the engine? I mentioned that you need to ensure the proper proper temperature, maintain proper temperature between 90 Celsius to around 120 Celsius within your engine for it to run smoothly, right? So to ensure that proper temperature is maintained, you need to cool your engine. There are two primary methods that you can use. One is to use air cooling and the other is to use liquid cooling, right? So air cooled engines, you can identify them easily. You can see the fins, right? So if you look at this, you can see sort of thin metal plates around the engine, which you call fins. So if you see fins, that means it is air cooled, right? It is being air cooled. So air cooled engines are mostly common in only in motorcycles, right? One cylinder small engines, you might see air cooled engines, but in vehicles, what you have here are liquid cooled engines. You have a evaporator, you have your cooling jacket, you have your condenser and the water pump, right? So you need to use a coolant to cool your engine. Then you can classify engines depending on the camshaft location, right? So there are several methods. Some engines have the cam inside your engine block, which we discussed previously in the previous two slides. You might remember we had the camshaft within the engine block, right? So that we call a cam in block arrangement. Then you may have a single overhead camshaft. You have only one camshaft and it is located on top of your engine, right? So this is a cam in block arrangement. The camshaft is found within the block and you have a push rod, a metal rod, right? And it is mounted, the rocker arm is mounted onto the push rod. So when the cam lobe hits, the push rod is pushed upwards and the rocker arm is pushed downwards. It's a simple lever mechanism, right? Operating in a simple lever mechanism. So when the push rod moves up, the rocker arms gets pushed down. When the rocker arm gets pushed down, your valve is pushed down, right? So your valve opens basically. So that is a cam in block arrangement. Then what you have is here is a single camshaft arrangement, single overhead camshaft. There's only one camshaft located for both the inlet valves and the exhaust valves. So also you can have a dual camshaft arrangement, which is I would say a little bit common now. I Mostly what you see in today's commercial vehicles are SOHC vehicles, which is single overhead camshafts, or DOHC vehicles, dual overhead camshafts. In dual overhead camshafts, you have individual camshafts for the inlet, for the intake valves and for the exhaust valves. Okay. Then depending on the fuel type, right? So conventional fuels, we have gasoline and diesel, petrol and diesel. There are some new engines coming up with alternative fuels which have the capability to run on two fuels, which we call dual fuel engines, and which can run on liquefied petrol gas, LPG, some alcohols like methanol and ethanol, biodiesel, and CNG, compressed natural gas. So depending on the fuel type, you can have different types of engines. Then the method of ignition. You have spark ignition engines, which are basically compression ignition, which are basically spark plug included. And without the spark plug, we have diesel engines, which are compression ignition engines. Then depending on the number of strokes. So some engines have only two strokes, while the more common, mostly used engines have four strokes. Okay, so depending on the number of strokes, just excuse me for 1 minute. Okay, so if you think about the classification based on the number of strokes, so this is how it looks like. If we first focus on the two-stroke engine, you have your intake, compression, combustion, and the exhaust. So the cylinder goes up and down. So it goes up and down you have two times, right? So during those two, you have one power stroke. Every two times, you have one power stroke. Out of the two strokes, you get one power stroke. It goes up, then the power stroke, exhaust happens, intake and compression, power and exhaust. So intake and power and exhaust. So let's start. Intake happened, compression happened, power happened, exhaust happened, right? You can see the flow. Intake blue comes in, compression, combustion red, and exhaust happen, right? So there are four things happening in two strokes. Intake and compression occurs when the cylinder is going up, and power and exhaust happens when the cylinder is coming down. Okay, can you see? When the cylinder is going up, when the cylinder is going up, the intake and compression happens. When it comes down, the exhaust and power happens. So those are the two-stroke in a two-stroke engine. In a four-stroke engine, the situation is much different. You have four strokes. So basically, you start from the intake stroke and then compression, combustion, power, and exhaust, right? So you have clearly have four stroke: intake, then compression, then the power stroke and the exhaust stroke. So you have clearly four different strokes. So only out of the four strokes, you only have one power stroke. So the piston goes up and down four times, but you get only one power stroke, right? So this is the comparison between the two. If we think about it, the two-stroke engine can provide power better. Why? Because out of the two strokes, you get every one power stroke. So in a four-stroke engine, out of the four stroke, you only get one power stroke. So out of the four strokes, for all the other three strokes, you need to provide energy by using the crankshaft, right? So if we consider in terms of power, the two-stroke engine can deliver a higher torque and power for the same design parameters, right? Same design capacities. But we do not use two-stroke engines. Why? Because the emissions are higher, the losses are higher, and you have the risk of mixing the engine lubricants within the combustion chamber, right? You can see there are no valves in a two-stroke engine. A two-stroke engine is what you call has a port, right? This is the intake port. Here is the intake port and this is the exhaust port, right? So there is no gate or a valve closing this. Only due to the piston it is blocked. It is being blocked due to the piston, right? Otherwise, it is always open. So there are no valves in a two-stroke engine, and what you have are called a port, right? So in a four-stroke engine, you have valves which keep everything in control. So therefore, you have less emissions and more efficiency out of the four-stroke engine, and there is no risk of any lubricant mixing with the fuel, right? Therefore, to reduce emissions and increase efficiency, we go for a four-stroke engines. That's why you do not find commonly two-stroke engines. The only vehicle that used two-stroke engine commonly was the tuk-tuks or three-wheelers, right? So after 2008, two-stroke three-wheelers were banned in Sri Lanka. And there might be two-stroke ships because of the higher torque, which does not run on petrol or either diesel. In most cases, it will be running on some alternative fuel like hydrogen, ammonia, or some carbon zero, like natural gas, likewise. So rather than relying on petrol or diesel, larger engines may run on two strokes, but the fuel might be different. Okay. So two-stroke engines you might find in chainsaws, grass cutter sort of applications, right? Because you need to have higher power. You might find a two-stroke engine in those sort of scenarios, right? Not in vehicles. Okay, so then we come to the innovations or future trends, right? So then we can, one of the future trends is the hybridization, right? Making cars, a portion of the car rely on electricity, right? So hybrid vehicles basically have two power sources. One is the engine, the other being the battery, right? Hybrid vehicles have two power sources, the engine and the battery. So hybrid vehicles itself is a large topic. I'll try to give you a slight overview on the hybrid vehicles. There is a degree of hybridization, right? We have micro hybrid vehicles, we have mild hybrid vehicles, we have full hybrid vehicles, and we have plug-in hybrid vehicles, and finally battery electric vehicles, right? So in each stage what you're doing is you are increasing the component, or you are increasing the percentage which you are relying on your battery, right? So micro hybrid and mild hybrid, the reliance on the battery is very minimal, especially in micro hybrids. When it comes to full hybrids, you have certain amount of relying on the battery. Plug-in hybrids and EVs, of course, rely on a major portion, can rely a major portion on the battery. So out of all these scenarios, what enabled the engineers to go into this hybridization is the engine efficiency. So they came up with a cycle. If you remember, we talked about the Otto cycle and the diesel cycle. So engineers came up with the cycle called the Atkinson cycle. We call the hybrid vehicles runs on the the principle of operation is the Atkinson cycle. There are some slight variations depending on the manufacturers. There are some cycle variations we call Miller cycle, Davis cycle. Likewise, there can be some variation, but the core principle is what you call the Atkinson cycle. So the difference between the other cycles and the Atkinson cycle is that you have shorter intake stroke and the exhaust stroke. The stroke length in the intake stroke and the exhaust stroke is shorter, but the power stroke, you have a longer power stroke, meaning you can get out more power and limit the energy wasted or used during the intake and exhaust stroke. So basically, you are reducing the input and increasing the output. So if you think in terms of the efficiency is basically the ratio between output and the input, right? So you are reducing the input and you are increasing the output. So you are reducing the denominator and increasing the numerator, meaning you will get a higher total value, right? If you think about a fraction, you are reducing the denominator and increasing the numerator. So basically, you will get a higher answer. That is what is happening in the Atkinson cycle. There is a disadvantage in the Atkinson cycle, it being that at low RPMs, the torque generated by the engine is not sufficient, right? So in hybrid vehicles, you might have noticed if you have driven one, at low RPMs, the car does not get much, the engine cannot generate a lot of torque. So this can be mitigated by using the hybrid system. Basically, what you do is you incorporate the electrical motor, right? So the electrical motor can supply you the additional torque which is required for the engine. And you run the engine without revving. You try to run the engine at the optimal efficiency point at all stages, right? The engine is most efficient for a particular RPM, right? So you can keep the engine running at the optimal RPM. This is why some people call that the hybrid engine is loud or it is revving all the time, right? So it is designed to run on the optimal RPM and maintain proper efficiency. So if it generates additional power, it will store that energy in the battery. And when you require additional energy, you can get it from the battery without relying on the engine, without straining the engine. You can mitigate with the battery system and the electric motor and achieve a certain degree of hybridization. So this invention or this principle allowed the hybrid vehicles to become popular, and they are becoming increasingly popular. Right. So in the hybridization is the difference, if you consider from 2 to 3, it is still a constant volume process, but the 4 to 1, the exhaust process or the exhaust cycle has been exhaust process actually has become a constant pressure process. If you remember previously, it was a constant volume process, but now from 4 to 1, the exhaust also occurs at a constant pressure as a constant pressure process. Okay. Then if you remember when we were discussing about the efficiency and the compression ratio, right? I mentioned that some manufacturers does achieve high compression ratios without engine knocking, right? So this is one such technology which has allowed manufacturers to achieve high compression ratios and eliminating engine knocking. So that one of such technologies we call the variable valve timing technology. Depending on the manufacturer, the method they achieve the variable valve timing will vary, right? So I have given here or stated here some of the most common systems which you will find in the common general market. But even for these manufacturers, there are other methods which they use, okay? These are not the only systems that these manufacturers are using, or neither these are the only technologies that are available in the market. Depending on the manufacturer, there can be a large number of methods that each manufacturer uses to achieve the variable valve timing. So variable valve timing, what it does is at high engine RPMs, you need to inlet your fuel air mixture faster, right? And you need to time your combustion critically or at a certain exact point to achieve the maximum power stroke and to get rid of engine knocking. So to achieve all of these three conditions, the manufacturers came up with a process that lets the car to decide on the valve opening time based on the engine RPM, especially at high RPMs. So variable valve timing, intelligent variable valve timing, a system introduced by Toyota. One of their systems is to rely on hydraulic pressure. So you have your camshafts in a hydraulically pressurized system, and due to the hydraulic pressure, you can advance your camshaft. As the pressure builds up, the camshaft will be advanced. Advanced meaning the time taken to open the valve is becoming shorter, or it is brought to forward, right? It will now open quicker. That is the meaning of advanced. And retard means make it uh, slower, right? It will open late. That means it is retard. So advance means at high temperature, what you need to achieve is to advance the valve opening. So one method Toyota came up with was to, by relying on hydraulic pressure, they advance the camshaft. And alternatively, Honda calls their system the VTEC system, variable valve timing system. So in the Honda, what they have is two cam lobes, right? So at higher, which have on the same camshaft, they have two cam lobes. So cam lobe is this shape, right? It has a slightly peculiar shape, right? It's not an even disc, right? Yeah, one side of the disc is eccentric, right? It is pushed outwards. So we call it the cam lobe. So Honda, what they do is they have two cam lobe shapes. You can see the orange cam lobe has a much larger surface, much protruded surface rather than the blue cam lobe. So when at higher speeds, what will be deciding to open your valves is the orange cam lobe, not the blue cam lobe. You have many videos available on the internet which you can look into to understand these concepts, right? So VTEC at high RPMs, you have a different cam lobe responsible for your valves, right? So that will also advance your valve opening time. And depth as well. Depth meaning how much does it open, right? From the cylinder head, how much of a depth is it opening? So Venus from BMW, they use a fully sort of an electromechanical concept. You have an electrical motor and sort of a mechanical linkage between the valve, right? So as the motor actuates, it has a threaded shaft which rotates with the motor. As it rotates, the shaft rotates and it advances the valve, pushes on the valve. So this system is slightly more complex rather than the other two systems, but it gives the additional advantage because you can control the time where the valve opens. You can control the depth of the valve opening, and you have full freedom of controlling the valve independently of the engine, right? So it's an additional advantage. And also not mentioned here, some engines like very high performance engines like from Koenigsegg, they have introduced hydraulically actuated valves, right? So if you see here, all the valves here are actuated mechanically, right? Due to the mechanical connection between the camshaft and the valve tip. But by what Koenigsegg is planning to do is get rid of all of this, right? Camshaft, rock arms, springs, they get rid of all of these valve arrangements and introduce a hydraulically actuated valves. That itself brings a much higher advantage because you are getting rid of all this unnecessary weight. All of these are made out of metal and they weigh a lot, right? So if you can get rid of this, all of this, you can achieve a significant advantage in terms of the weight loss, right? So as the engine gets lighter, you can produce more torque, more power out of a less weight. That's also an advantage. So there, if it is hydraulically actuated, you have gained the full freedom of controlling the valves from the hydraulic pressure, right? So there are some other technologies and methods used by different manufacturers which you can look into. Okay. Then talking about alternative fuels, one alternative fuel which is gradually becoming popular is hydrogen. So one type of hydrogen implementation is hydrogen fuel cells. So hydrogen fuel cell is not an internal combustion engine. It is an electric engine, electrical vehicle, basically. So what does the fuel cell does is it breaks down hydrogen and oxygen and converts it into H2O. When it is converting into H2O, you get the chemical reaction generates a certain energy. You get it as the electrical energy, store it in a battery and run a motor. And your resultant is just water, right? Out of a hydrogen fuel cell vehicle, the exhaust is water, so it is sustainable. But the storing and transportation of hydrogen is not easy, right? So hydrogen is actually a rocket fuel. So it is highly combustible. So keeping it safe is not easy as it looks. Therefore, you need cryogenic temperatures. Cryogenic meaning very, very low temperatures, right? So it is not easy to achieve cryogenic temperatures. Therefore, it is not very popular in countries like, full developed countries like Japan, and I think some regions of Australia and USA. They have only some states only has the access to hydrogen and hydrogen fuel cell cars. Also, some manufacturers like Toyota and JAC and some other manufacturers, right, are looking into the possibility of hydrogen combustion engines. They have run several cars in the 24-hour races, right? They have completed 24-hour races in a Toyota Corolla hatchback, which is seen here. They have run a hydrogen combustion engine for 24 hours. So there is a potential, but the limitation being for the hydrogen combustion also, there are high pressures involved. Therefore, you need to reinforce your engine block, right? So your engine block should be able to withstand the pressure under combustion. Therefore, you need stronger engine blocks. So it is not cheap. To make the engine block stronger, you need more strength, materials with more strength. That will be costly, basically. So it is still being researched, and we'll be seeing in the upcoming future, maybe ammonia combustion engines. We don't know. There are still research going on about these topics. Okay, then this is a little bit more which could come into practice in the early future, right? So the six-stroke engine. Originally, the patent is with, I think, Porsche. So they have developed a strict six-stroke engine. So what we have today are two and four-stroke engines. Out of that, also we only use the four-stroke engines. So Porsche has come up with the six-stroke engines. Also, Mazda is also on the research way, doing research on this topic. So what is basically the six-stroke engine is simply it is a combination. It looks as if a combination of a four-stroke engine and a two-stroke engine. So you have your intake stroke similar to a four-stroke engine. Then the compression occurs, right? You can see the depth of the intake stroke is only up to here, and the compression occurs. Then the with the combustion the power stroke occurs, but the specialty being your power stroke is again longer than your intake stroke, right? So during the power stroke the piston head moves to a bottom like this. The BDC, bottom dead center, lies around a region like here. So when the piston reaches the bottom dead center, you can see here there are two ports, right? There are no valves, there are two ports. So these two ports will inlet new air fuel mixture to the cylinder, and by opening the exhaust valve, you can get rid of the exhaust gases from this third compression, third power stroke, where you created the exhaust gases. During the fourth process, you have the intake while the exhaust is also occurring simultaneously. Now you have a longer compression stroke, and the combustion stroke occurs, and you have the power stroke and the exhaust stroke. So likewise, it is a combination. It seems as a combination of the four-stroke engine and the two-stroke engine. So that ends up being a six-stroke engine. Then what we have is the Wankel engine. This itself is not a something new, right? We had Wankel engines from the early days, right? So we call the rotary engine or the Wankel engine. So the Mazda RX-8, I think RX-7, not RX-7, RX-8. So had the Wankel engine or the rotary engine. As to why the Wankel engine or the rotary engine is not popular is because of the high emissions. It is not as efficient, and it is there are high emissions. You are mixing the fuel and the exhaust gas with time, so it is not efficient. You are burning a lot of fuel. Therefore, the Wankel engine was not highly popular with the car manufacturers. The only popular car model was the RX-8. But Mazda has not given up. They are doing their research on the Wankel engine, and what they have initiated is to keep the Wankel engine or the rotary engine as a generator, right? So the engine itself does not drive the vehicle. The engine is not connected to the wheels. The engine is connected to a generator. So when the engine rotates, it runs the generator and generates electrical power. This electrical power is stored in the battery and supplied to the electric motor. So it is sort, we call that arrangement a series hybrid vehicle, right? So when we are talking about hybrid vehicles, we can talk about series hybrid vehicles, parallel hybrid vehicles, and the combination of series and parallel hybrid vehicles. That is the hybrid architecture. That is based on the hybrid architecture. We can categorize hybrid vehicles into three categories. One being the series hybrid vehicles, one is parallel hybrid vehicles, and the last one is the combination between the series and parallel hybrid vehicles. So the BMW i3 has a version which is a series hybrid vehicles, and mild hybrid vehicles like the Honda Insight, the early Honda Insight. I don't know about the latest one. And some Honda CR-V models were mild hybrid vehicles, right? And series parallel hybrids are like Toyota Aqua, Toyota Prius has or runs on the series parallel architecture. So what Mazda is developing is the series hybrid architecture. The engine is not connected to the wheels. What runs the wheels, what provides power to your wheels are the electric motor. So in the future, Mazda plans to introduce a vehicle to the market like this. Is still a concept car, not a marketed vehicle, which has an engine not connected to the wheels, runs the wheels on the battery and the motor. Okay, so the engine only acts as a generator, minimizing losses. So when the engine acts as a generator, you can reduce lot of losses. Okay, there are no fluctuations in the load. You can just run the engine on the maximum or the optimum RPM, and you can get rid of lot of losses. That's why Mazda is researching on this. And if you look at the Wankel engine itself, you get rid of the reciprocating motion. I don't know whether you notice in the Wankel engine, there is nothing going up and down. It is from the beginning itself, it is a rotary motion, right? So you are converting rotary motion again into a rotary motion using the crankshaft. So you can reduce some sort of a mechanical energy losses there, but still the efficiency is not enough for commercialization. Okay. So yeah, that's on the innovations, and that brings us to the end of the session. Thank you for your participation and your kind attention. And if you have any questions, you can ask them by unmuting yourself or by putting it on the chat. So thank you and have a good night.
Thank you for that highly informative and insightful session. We will now open for the Q&A session. Participants are welcome to unmute themselves or directly send your questions to chat. So there's a question. They're asking in modern internal combustion engines, what are the most impactful auxiliary systems that improve efficiency and reduce emission, and how do they work together?
Sorry, Litila, I think the question was on auxiliary systems, right? What is the most important?
Yeah.
So the term auxiliary system is slightly ambiguous in terms of an internal combustion engine. So I do not like there are many systems running parallel to the internal combustion engine having different purposes. So if you want to study the auxiliary systems, you need to do a different analysis. So if you mean systems which help the internal combustion. So the turbochargers, superchargers likewise, right? So turbochargers are a good addition to the engine, which can improve the engine performance. So the purpose of the turbocharger is basically improving the air intake, right? So the turbocharger does not rely on outside energy. You do not need to provide any energy to the turbocharger. What the turbocharger does is uh, from your exhaust gas, when your exhaust gas is expanding, it runs the turbocharger. As the turbocharger runs, or the turbine side, more specifically, your turbocharger has two sides. One is the turbine side and the other is the compressor. So your turbine side is located at the exhaust manifold and your intake manifold has the compressor. So as the exhaust gas expands, your turbine runs from that energy, and your turbine and compressor are both on the same shaft. So as the turbine rotates, your compressor rotates in the inlet manifold, thereby compressing your air intake so that you get more oxygen into the cylinder, basically making more combustion more efficient. So what that is, turbochargers are one such system that makes the internal combustion more efficient, and also the superchargers. So the superchargers are different from turbochargers. Superchargers does not have a turbine. The supercharger relies on your engine power, right? It is connected to your flywheel or the crankshaft, right? So from the engine itself gets the power, and rotates the compressor in the inlet manifold. Again, doing the same thing, it increases the intake pressure, right? But the advantage between the two, the turbocharger has what you call a turbo lag, right? So there it takes a little bit of a time to build the exhaust gases. So during that period, the turbocharger will not run. But the supercharger can run even at low RPMs. If the engine is running, your supercharger is good to run. So therefore, there's a slight advantage in terms of that. But again, a disadvantage because your supercharger relies on your engine power, but your turbocharger does not rely on your engine power. So there are disadvantages and advantages, but both systems help the internal combustion engine. I hope I answered your question. Yeah, so I have received one question regarding the global shift toward electric vehicles. Yes, electric vehicles does get an advantage, but also there is a all of these systems, like I said, there is no perfect answer, right? Every system will have its own advantages and disadvantages. Yes, the internal combustion engine has emissions, but so does the electric vehicle. So, according to recent researchers, when you drive an electric vehicle just out of the dealership, you are carrying 2 years worth of emissions from an internal combustion engine vehicle. So you have to drive your electric vehicle for 2 years without without any grid power charging. If you solely rely on solar charging for 2 years, then you can call the electric vehicle truly as zero emissions. So when you are developing the battery, you have emissions, right? You are mining for lithium, nickel, cadmium. These metals are not commonly found on the surface of the earth. You have to mine for them. So to mine, you need internal combustion engine vehicles. So even though the electric vehicle seems like zero emissions, there are indirect emissions due to the electric vehicles, right? So yes, they reduce the emissions. They do perfect answer. Hybrid vehicles has the best of the both worlds, right? So maybe we still don't know. We can go for a certain degree of electrification, but still we don't know whether 100% electrification will be the answer, right? So there will always be the balance between the both worlds, right? We will rely on a certain percentage with electric vehicles and a certain percentage on internal combustion vehicles. I'll add a little bit more to that question in terms of countries like Sri Lanka. Yes, since Sri Lanka is a small country, many EVs have the potential to electrification, right? So if we have a good electric charging grid, we can get a major advantage in terms of electrification. Thank you.
With that, I think that's the end of the Q&A session. Thank you, sir, once again for sharing your valuable time and expertise with us today. So now to deliver the word of thanks, may I kindly invite Mr. Devidu Herath, YP Activities of IET On Campus-KDU. Over to you.
Good evening, everyone. It is my great pleasure and honor to deliver the vote of thanks for today's insightful webinar on internal combustion engines and their auxiliary systems, from fundamentals to real-world applications. First and foremost, I would like to express our sincerest gratitude to our distinguished guest speaker, Engineer Hiran Rajasuriya, lecturer at the University of Moratuwa. Thank you, sir, for sharing your valuable knowledge, practical insights, and real-world experiences. Your session has undoubtedly deepened our understanding and inspired us to explore the field of automotive engineering further. I would also like to extend our appreciation to our moderator, Mr. Lithila Manulaka Herath, for guiding today's session so smoothly and ensuring an engaging and well-structured discussion. Our heartfelt thanks goes to organizing body IET On Campus-KDU for planning and executing this webinar successfully. Your efforts in creating such out to all the participants who joined us today via Zoom. Your presence, enthusiasm, and interaction made this session meaningful and lively. Finally, we are grateful to everyone who worked behind the scenes to make this event a success. With that, we come to the end of today's session. We hope this webinar has been informative and valuable to all of you. Thank you once again. Have a great evening.
So before we conclude today's session, I would like to invite you to take a group photograph with